Welcome back, folks. Short video. We can combine impedances when they're in series and when they're in parallel, just as we can the other components. So this should feel familiar to you from those videos, and they behave nicely. Remember, capacitors are the backwards ones. Only capacitors. Okay, so if we have two impedances in series, and we're going to start using these blocks again, because it might be a resistor, it might be a capacitor, it might be a resistor, a capacitor, an inductor, all wired in different ways. It has some impedance, Z1. So we'll use these blocks just to mean some collection of components that have an impedance that we're working with. Okay, again, in Europe, those would be resistors, but in the US, we're going to abuse them to just mean some general component that we're not sure of. Okay, when they're in series, we have the combination of the two, ZAB is equal to Z1 plus Z2. Okay, the impedances just add when they're in series, just like resistors, just like inductors. Okay, these are all the ones that play nice. When they are in parallel, okay, stick two of these in parallel. We have to take the inverse. Okay, and the inverse of impedance is something called admittance. Okay, so if this is Z1 and this is Z2, and we want to know what this combination creates from A to B, then the admittances add. I'm not entirely sure I spelled that right. Correct me in the comments. Okay, the admittances add, and admittance, the variable, instead of Z is Y, and the unit is the Siemens. Okay, capital S after the German guy. Okay, since for impedance, not sure I've said this yet, impedance, the variable is Z, if you didn't figure that one out. And since it's volts over ohms, the unit, I'm sorry, since it's volts over amps, the unit is ohms. Okay, so if we're going to invert it, just like we did before, then we're going to end up with the same inversion, the Siemens. Okay, so the admittances add, so we can say YAB equals Y1 plus Y2. Right? I think we've played this game a few times already. So it's going to be 1 over ZAB equals 1 over Z1 plus 1 over Z2, which we can solve and find that ZAB is equal to 1 over Z1 plus 1 over Z2. And if we have more than 2, we can add terms on the bottom. For only two impedances, we can use product over sum. Okay, Z1, Z2 over Z1 plus Z2. Look familiar? Okay, so we've really run through 4 types of components. I'm going to leave sources out for this one, but we have resistors, inductors, and impedances, which I guess isn't a component, but describes components. And then we've also talked about capacitors. Okay, when these are in series, all of these, we add them. Okay, when they're in parallel, the inverses add. So add inverses, or do product over sum if there's only two. Okay, the oddball is the capacitor. Okay, almost like it just needs to do its own thing. Add the inverses. Hold on, we're going to cheat. Cut and paste our way to glory. Okay. So we're going to add the inverses when capacitors are in series, and we're going to just add capacitors when they're in parallel. So they're backwards, right? Just flip those columns around. And that's it. Okay, so we can reduce circuits the same way we did, whether they're impedances or resistors. So if we can work with impedances, we can do all of the same circuit analysis that we did before. We can use the voltage divider. We can use the current divider. We can do KVL, KCL with phasors. We can use mesh analysis, nodal analysis, you name it. Everything we did in the first part of this class, we get to do it again with inductors and capacitors, but we got to use complex numbers. So that means phasors for our voltages and currents, and impedances for our passive components. All right, I want to analyze some circuits. It's almost like it's the title of the class. Maybe that's what we should get going. Okay, so how do we use all of this stuff? How do we use it all to analyze a circuit? That's what's coming up next. Stay tuned and good luck.